And that would be good. It will be easy. The topic, this is in book section 3-3, long division of polynomials. No, that's what it is. That's what we're going to look at. It's division of polynomials, dividing polynomials. Okay, so we're just going to start and look at something everyone should have learned. I don't blame you if you haven't, because I hear there's a movement to eliminate this. But what if we were to want to divide a number, say by 5, using long division? Okay, we have a process. We look at the first digit, we see, okay, how many 5s are in there? Just 1. We multiply by 5 by 1. We subtract. We bring down the next digit. Now I've got 43. We look at that and go, oh, 8. 8 times 5 is 40. Bring down 3 and we get 5. Look back to 7. Bring down 7. And we're almost done. We have now at the bottom 2, which we can either write remainder 2, or we could write that as 2/5. Now, I don't want to embarrass anyone, but if anyone feels weak in this, you could let me know. This is the basis for what we're going to be doing. What we're going to be doing actually is a little easier if you're very careful. You don't actually have to figure out, oh, how many times does 5 go into 43 or 35 or whatever, generally speaking. But division of polynomials looks very similar. So if, for example, I had 6x squared minus 26x plus 12, I set it up the same way. Now, for purposes of being really careful, I would suggest instead of writing minus 26, write plus minus 26x. Reason being, we're going to be dealing with columns here, and we want to be clear that this is a minus 26. And we're going to divide it by x minus 4. It's also important if one of these terms is missing, like this, there's a 0, you put it in anyway. 0x if necessary, or 0. Okay, let's do the same process, only with a little more knowledge of algebra. I'm going to divide x into 6x squared. That's going to go in 6x times. Or if you like, just think, well, 6x times x is 6x squared. That's what you need to do. 6x squared. I'm going to do that same thing, plus minus here, because it's going to work out better. Minus 24x plus minus 24x. Now I have to subtract. And of course I have to be careful when I'm subtracting a negative, because subtracting a negative is adding a positive. So minus 26 plus 24 is minus 2x. Okay. What goes here? Minus 2. Minus 2 times x, and down to 12. Minus 2 times x is minus 2x, minus 2 times minus 8 is 8. Subtract, I get 4. I have my remainder of 4, or if I like, 4 over x minus 4. That's it. That's the basic process. I'm going to do one more example, a little more complicated. We're going to divide 8x to the 4th plus 6x squared. So I'm going to put 0x cubed plus minus 3x plus 1. And I'm going to divide this by 2x squared plus minus x plus 2. Right. Someone tell me what's going to go here. What's the first step going to be? 4x squared. Now what's really nice is all you have to do is look at the first term. Thank you, whoever said that. All you have to do is look at the first term. You don't have to worry about these yet. Right? 8x to the 4th. This is minus x, right? 4, okay, so, oh wait a minute, where is that going to go? Negative 4x cubed. You see why I put in the 0 here. I'm going to need that column. And now 8x squared. When I subtract, I'm always going to get a 0 here. 0 minus 4 is 4x cubed. Minus 2x squared. And I'll bring down the next term. Okay, 2x squared into 4x cubed. Pretty straightforward. 2x, 4x cubed, minus 2x squared, plus 2x. Minus 2 minus 2 plus 0, right? This is just x plus 1. Now, because this is lower degree than when I'm dividing, I'm done. So I could either say remainder x plus 1, or I could say x plus 1 over 2x squared minus x plus 2. The point here is you want to keep careful track of the missing variable here, where things go in the columns. Now, another important thing about this example is you can see it doesn't matter. This can be any polynomial you can divide into any other polynomial. I mention that because we're going to go over another optional method called synthetic division, which doesn't have that flexibility. You can only divide x minus some number, x plus negative of some number. But you'll see, especially if you learn it, or you knew it already, and you have it in the field, it's very convenient, it's very simple, and simple is always good because you tend to make less errors. So, while you can always use this long division method, I won't require you to do synthetic division on an exam. You might want to. All right. see how synthetic division works. So we're going to do this problem. 2x cubed minus 7x squared plus 5 over x minus 3. So here's how you set it up. The number you're subtracting here, 3, goes over on the left. The coefficients, all of them, even the ones that are missing, go over here. So we've got 2 minus 7. We're missing x. We don't want to miss it. 5. Step 1, just take down the first coefficient over here. And now the process gets really easy. You're going to multiply the number here by 3, put it here, and I'm going to add. Intentionally being repetitious, I'm going to multiply the number here by minus 1. Add. Multiply this by minus 3, minus 9, and add. It's just really straightforward. You multiply two numbers and then add two numbers. And you do that until you're done. Now we have to know, well, what is this result? Well, over here on the right is the remainder. You either write, remainder minus 4 or minus 4 over x minus 3. These numbers are the coefficients. 2x squared minus x minus 3. That's synthetic division. It's really nice technique to know. Again, because you do have to be careful about columns. You do have to remember to put in the extra missing coefficients. But it just multiply, add, multiply, add, multiply, add, and you get the result. I was wrong. This is the chapter that's really heavy duty. All right, so we're going to go over some stuff that actually is pretty tough here. It's probably important to know the theorems. It's not important to know the proofs of the theorems. I'm going to leave this up here because we'll use it as an example. First theorem is called the remainder theorem. Says that if you divide some polynomial by x minus c, that the remainder is just going to be p of c. In other words, the value of the polynomial if you plug in c. See what we mean by that here. Let's say this is our p of x. 2x cubed minus 7x plus 5. And I want to divide by x minus 3, but I really only want the remainder. Well, I can say 2, 3 to the 9th minus 7, 3 squared plus 5. that's, where is that backwards, didn't it? 9. Oh, what am I doing here? 2 times 3 cubed minus 7 times 3 squared. Okay, so what's 3 cubed? That's 27, right? 54 minus 9 times 7 is 63 plus 5. So this is 59 minus 63, or minus 4. Is that what we got before? Okay, so this, you can see how this theorem could be really useful. All right, so we want to know why this is the case. Well, we want to divide px by x minus c, and we want to get a quotient polynomial and a remainder. So we could rewrite this as see if I can connect this. If I divide this equation by x minus c, we get px times x minus c equals quotient plus the remainder over x minus c. Just like division of numbers. Right? We then plug in c here, what do we get? Well, this is 0, so this is just r. That's the whole proof of the remainder theorem. Okay, one more example. What if we want to know the remainder when we divide 3x to the 5th plus 5x to the 4th minus 4x cubed plus 7x plus 3 by x plus 2. Well, our c here is not 2, right? Our c is minus 2. Plug that in. So 3 times negative 2 to the 5th plus 5 times negative 2 to the 4th minus 4 times negative 2 to the cube plus 7 times negative 2 plus 3. 2 to the 5th. I tried to mention this in this class. Computer scientists, you all want to know this. You want to have these at the tip of your tongue, because you're going to be working in binary. Anyone know off the top of their head 2 to the 5th? Yeah, you can also like 2, 4, 8, 16, 32. You can do that until you get it. But there's a minus, so minus 3 times 32 is minus 96. 2 to the 4th, we can forget about the minus, right? That's 16 times 5 is 80 minus, okay, we're going to have an extra minus, so it's going to be plus. 8 times 4 is 32 minus 14 plus 3. All right, 96 minus 14, that's a convenient 110. 80 plus 32 is 112 plus 3. So this is just 2 plus 3 is 5. remainder we'll get, for sure. Second theorem we're gonna look at, which I think will be even more useful. It's called the factor theorem. To show the factor theorem, we're going to use the remainder theorems to make it real easy. It says C is the zero of P of X. And I think I talked the other day about this idea, IFF, if and only if X minus C is a factor of P of X. All right, so this is actually, you can think of it as two theorems. C is, if C is a zero of P of X, then X minus C is a factor of P of X. That's one theorem. If X minus C is a factor of P of X, then C is a zero of P of X. This is heavy-duty stuff. I just want to make sure what I'm saying is really clear. I have some polynomial. I'll just write it this way. And if I have some numbers, well, I want to use C here. I'll use R for root. If P of R is 0, then I can divide this by X minus R and leave some other polynomial. Furthermore, if this is a polynomial, if these two polynomials, these two factors multiply together to get this, then R is a root of this. So we're going to prove both of those. So the first step is we use the remainder theorem. We say P of X equals Q of X times X minus C plus R. So if C is a zero of P of X, that means P of C equals 0. Then it means equals Q of C times C minus C plus R. Well, this is clearly 0. C minus C is 0. So we have 0 equals R. That means if you divide this P by X minus R, let me rephrase that. Since C is a 0, the remainder when you divide will be 0, which means it's a factor. I said a lot there. I'm trying to say that again. I have some polynomial. I discovered that for some C, this is 0. That tells me if I divide this by X minus C, my remainder will be 0. So that means it's a factor. No remainder. So that's part one of the theorem. Guess I'm going to have to sidle over here. So if we assume c is a 0, we find that x minus c is a factor. Now we go the other way. What if x minus c is a factor of p of x? That means p of x equals some quotient times x minus c. But if that's the case, what is p of c? It's q of x times c minus c, which is, of course, since this is 0, is 0. So if c minus x is a factor, then it's c is a 0. What if anybody looks at this and goes, duh? I mean, this is kind of the underpinning of something we've been doing for a long time. We've had like a quadratic. And quadratic equation. And we factor it. Well, these factors tell us what the roots are, right? We take one of those roots. Of course, if we plug it in, we're going to get 0. That was the whole point. All right. You know, I'm gonna cheat here. The next section in the book, which you are welcome to look at, it's just not going to be important in this class, goes through why these theorems establish synthetic division. And I just feel like it's just too much right now. It's not necessary, it's just too much. I'll just give you the key insight, which is at the end of the synthetic division, you've gone through the same process you go through to evaluate P of C. So essentially, you're using the remainder theorem. P of C is equal to the remainder. So, okay. I think that's one more thing I'm going to do with this, with these two theorems. Just do one example. Which will be a technique we're going to learn further on. Let's say I wanted to factor x cubed minus 7x plus 6. And I don't really know how to factor this. It's a cubic. Can't do anything nice with it. But let's say I just happen to look at it and think, I think one might be a 0. So 1 minus 7 plus 6, it's equal to 0. Knowing it's a 0, that tells me that x minus 1 is a factor. At which point I can divide either using synthetic division or long division. this out. X squared minus x cubed minus x squared, minus a minus is a plus, 7 minus a minus, minus 7 minus minus 6x plus 6, minus 6 minus 6x plus 6, remainder is 0. So now I know that the factors of f of x include x minus 1, x squared plus x minus 6. So the idea is if you want to factor something, you can guess one of the roots. You plug it in, you check, it's 0, so you know it's a root. You know that when you divide, it's going to divide equally. Now, here we've got quadratic. We need the quadratic formula to do this, or maybe we can factor this also using reverse FOIL. So 3 and 2, right? Plus 3 minus 2 is plus 1. So now we can see right away the roots of 1, 2, minus 3. So this is a strategy for dealing with factoring a polynomial greater than 2, greater than quadratic. All right, I think, like I say, I think that's enough for today. I'll be here for a few minutes if you want to talk about